Okay, hi. So I'm talking about. Uh, we're studying a fundamental class of distributions, these sums of independent integer random variables, and I'm interested in. We're interested in how do we learn these? What's their structure? So sums of independent integer random variables is a bit of a mouthful, so we use K-SIIRV for short. A K-SIIRV is a sum of independent, but not necessarily identical, distributions supported on the integers between 0 and k minus 1. A special case k is equal to 2 when the summands of Bernoulli's is known as a Poisson binomial distribution. These have been extensively studied. Now, the Poisson binomial distributions in particular have plenty of applications. K-SIIRVs too, there's plenty of work in the probability of statistics literature. Relatively recently, we've been interested in these things in computer science. So they have applications in game theory. Okay, sounds a lot to me. And reading more and in learning, which is the subject of this paper. Although these things have an interesting structure, we'll have some structural results on the way. So specifically, we're going to talk about. I'm going to talk about learning first, about the previous work and our results, then about the second main topic of the paper, which is epsilon covers for K-SIIRVs, and finally, I'm going to go into more detail on our algorithm for learning, which involves the Fourier transform, because that might be of general interest. Okay, learning. Specifically, density estimation. We have samples from a distribution that we know belongs to a certain class, in this case K-SIIRVs, and we want to find a distribution that's close to it, say within epsilon total variational distance. You recall total variational distance is half the L1 distance. And we're interested in doing so with as few samples as possible and within as little time as possible. Now, we can't just, if we try to learn an arbitrary distribution with the support of a K-SIIRV, which is about n times k, we need nk over epsilon squared samples. Note that when n is equal to 1, we actually have an arbitrary distribution over the integers between 0 and k minus 1. So we're going to need at least k over epsilon squared samples to learn this. And previous work has shown how to do this independently of n. So for k is equal to 2, there was a relatively fast algorithm, but it's not known how to get an efficient algorithm with the optimal sample complexity. And for general k, the best bound on the sample complexity is a high degree polynomial in k and epsilon, which is far away from this lower bound I mentioned earlier of k over epsilon squared. So the question is, what is the precise sample complexity, and what is the can we do for efficient learning? And what we get is we get a learning algorithm, which does get this k over epsilon squared sample up to logs, and the runtime is also a more sensible polynomial of k cubed over epsilon squared. Now, if you want to ask the question, are log factors in the sample complexity really necessary? It turns out the answer is yes. We can give upper and lower bounds on the sample complexity of k root log 1 over epsilon squared. Although for k bigger than 2, this for large k, this algorithm isn't efficient. It's exponential in k. For the special case, k is equal to 2, we can get an algorithm which has optimal sample complexity and running time as a constant factors. So this is how this compares to the previous work. So previous approaches to this problem, I've considered looking at the shape, for example, using log complexity for partial binomial distributions. This doesn't quite give the optimal thing. And for K-SIIRVs, K-SIIRVs don't satisfy any natural shape criteria. They're not unimodal. They're not. And another approach is epsilon covers. We can run tournaments over epsilon covers. But as we'll show later, you're not going to get efficient algorithm this way. Third idea is use central limit theorems when the variance is large, and do something else when the variance is small. And you could even do an arbitrary distribution learning for that case to give you something sensible, but not good enough for us. And previous papers have used these approaches, these Diakonikolas and Stewart, and for k is equal to 2 had the best results, and the same people with O'Donnell and Tan the next year. Our approach is somewhat different. We start with the Fourier transform. And most of our results consider the sparsity of the Fourier transform. And we give a novel and quite simple learning algorithm which works for distributions which have a sparse Fourier transform. And it works like this. Basically, we just learn the Fourier transform. We learn the discrete Fourier transform at points where it might be large, and then we give a hypothesis in terms of its Fourier transform. I'll give more detail on this later. First, the other main area we get results, epsilon covers. So an epsilon cover is so we want a set of distributions, preferably a small finite set, which any distribution in the class is epsilon close to something from the set. More specifically, proper epsilon cover is one where these distributions we're in this set are all actually in the class. Now, previous work on these, again, the k equals 2 case has better results. Diakonikolas and Padrichu give a constructive proper of this quasi-polynomial size. But for k bigger than 2, the best known bound is exponential in 1 over epsilon. And so the first question is, can we get something closer to this, at least for constant k? And the answer is yes, we can get quasi-polynomial for constant k. We have a bound of size order of n times 1 over epsilon to the k log 1 over epsilon. This slightly improves even the k is equal to 2 result best previously known. And this algorithm is constructive. This cover is constructive. We give an algorithm for outputting it, which runs in a similar time. And this cover size bound is tight. Turns out that any cover of epsilon SIIRVs, epsilon cover of k SIIRVs, must have about this size. So what are covers useful for? Well, we can use them for learning, specifically proper learning, getting outputting a hypothesis distribution which is actually a k-SIIRV. And we can easily do this given our non-proper learning algorithm and this cover in about this time. The k is equal to 2 case also has application in game theory. Diakonikolas and Padrichu give an algorithm for computing epsilon Nash equilibrium in two strategy anonymous games using their cover, and you can just drop in our cover and get a faster algorithm. I won't have time to go into detail about how the proofs for the covers work, but the main ideas are for the upper bound, we're going to give things in terms of the coefficients of the Taylor coefficients of the log Fourier transform expanded around various points. For the lower bound, the set of these distributions has interesting structure. We show that the set of all partial binomial distributions, or k-SIIRVs, as considered as a subset of the set of all distributions, all discrete distributions with the support, has a non-empty interior. In particular, we can construct a cover by taking a point deep in the interior and you can perturb it in many ways. and this will give you, this gives an epsilon packing. And similar techniques lead to the sample lower bound using Oswald's lemma. So, learning, so how does this learning algorithm work? And what does the Fourier transform have to do things? Okay, so if you call the Fourier transform, it's a complex valued function. It's given by this expectation. In particular, we're interested in the discrete Fourier transform. The important thing about this is that it only takes a finite number of values, and it's easy to invert. And why the Fourier transform? Well, when we sum independent random variables, we point-wise multiply their Fourier transforms. This means that if we add more random variables, the Fourier transform gets smaller. And in particular, this will means that the Fourier transform of a K-SIIRV is approximately sparse. K-SIIRVs also can have a periodic structure, which caused difficulties in previous approaches. And this shows up very simply in the Fourier transform. Okay, I need some pictures. So this is a binomial distribution. I dare say you've seen it before. This is the absolute value of its Fourier transform. Of course, Fourier transform is complex, but we're interested in its size. You notice everything here looks a bit like a Gaussian. Unfortunately, not close enough to use as a hypothesis for us. But the Fourier transform of a Gaussian is another Gaussian, but with the reciprocal of the variance. And this has the effect that, so this blue binomial has a larger variance. You'll notice that its Fourier transform has narrower peak. Also, because these distributions are supported on the integers, unlike Gaussian, we get this thing repeats every one. It has period 1. So you look at the effective support, the support in which we can ignore an epsilon mass outside. And for one of these distributions, by standard concentration results, we just need to look at root log 1 over epsilon standard deviations. Right? But we also show that we get a bound on the size of the effective support of the Fourier transform. Now this, just as the Gaussian had the reciprocal of the variance, this is going to be root log 1 over epsilon divided by the standard deviation. And now, in the learning algorithm, we're going to construct a hypothesis which is supported on the effective support. This means we only need to consider the discrete Fourier transform modulo the size of the effective support. So say that's m, which is going to be log 1 over epsilon sigma. And we basically consider m equally spaced points in between 0 and 1. How many of these are going to be in this peak? Well, the answer is the discrete Fourier transform is going to be large at only log 1 over epsilon integers. And of course, this effective support could be root n. So this is sparse. And our algorithm, essentially, we learn these log 1 over epsilon expectations, and that suffices. Okay, more completely, we estimate the effective support using the mean and variance, and then we estimate the empirical discrete Fourier transform, modulo the size of the support, but we only calculate it at log 1 over epsilon points. And everywhere else, we set the discrete Fourier transform to 0, because we know it's smaller than the distribution. And we output this sparse discrete Fourier transform, which is the sparse discrete Fourier transform of our hypothesis. Now, this is a bit of an unusual description of a distribution, but it's worth saying that it's useful. You can easily calculate the probability mass function just by inverting the discrete Fourier transform. And we can also sample from this pretty efficiently. Okay. So, K-SIIRVs. K-SIIRVs are a bit more complicated because they can have a periodic structure. So, simple example: if the individual random variables only supported on things which divide by 3, then so will the K-SIIRV. It has gaps, and when this shows up in the Fourier transform, now instead of repeating every 1, because the thing is only supported on integers that divide by 3, we repeat every third. And so this has Fourier transform is large at places that are far from 0. Okay, so this is a bit of an artificial example. We just add another distribution to this, we get something that's supported everywhere, but the discrete Fourier transform still has this periodic structure. It has sort of some kind of periodic structure. And it's large near 0, near a third, near 2/3, and each of these peaks is about log 1 over epsilon integers. So it's large, 3 times log 1 over epsilon integers. In general, discrete Fourier transform of K-SIIRV is effectively supported on k times log 1 over epsilon integers. But unfortunately, we don't quite know where these are, because we don't know which period. We know that the K-SIIRV has periodic structure with periods less than k, but we don't know which periods are more important. And what happens is that discrete Fourier transform is close to things, to these fractions of, well, m times a over b, which have denominators smaller than k. And they're k squared of those. So this k squared log 1 over epsilon integers, we know this thing might be large. And so our algorithm is compute these k squared log 1 over epsilon expectations to the empirical discrete Fourier transform. And then we have to do some thresholding. We truncate this, we throw away things which have a small discrete Fourier transform, as well as setting it to 0 outside the things we calculate. And this means we end up with something which only has k log 1 over epsilon integers, which is why we end up with this, this sample complexity. And again, we return the distribution with the sparse discrete Fourier transform. So to conclude, we give tight bounds on the sample complexity, on bounds on the computational complexity of learning K-SIIRVs. We give tight bounds on the size of epsilon covers of K-SIIRVs. We also give some nice probabilistic and geometric results on the way that I probably haven't been able to do any justice to with this talk because it's technically complicated. Open questions. First one is, can we apply this technique to other families? Because there's many of simple families of distributions that have sparse Fourier transform. And this algorithm is fairly general. In subsequent work, which I presented in Stock on Tuesday, we give a higher dimensional, we consider a higher dimensional generalization of Poisson binomial distributions, these Poisson multinomial distributions, and apply this to that. So the question is, what else can we apply this to? Can we do better with using techniques from sparse Fourier analysis, because we're just doing the naive thing here, which gives us k cubed. Can we do efficient proper learning? All we do here in terms of covers, we only have efficient algorithms for giving this strange description of the hypothesis. Can we get a K-SIIRV? And in subsequent work, for k is equal to 2, which I'm going to present immediately after this, we look at that problem. That's all for this talk. Thank you for listening.